All right, it looks like we are live. Hi, and welcome to another episode of Off Chain with Jimmy Song. And it's White Paper Wednesday, and I am going to go and read you BIP342. But before I do, I do want to make sure that my chat is okay and everything else. I don't know if everyone can hear me or not. It's please let me know in the comments or something or in the chat. I know this is I'm in London right now. I'm not using my usual setup, so everything's not quite as good as it normally would be, and so on. It does sound like everything is going through. So I'm gonna go through and read BIP 342, and we're gonna go through and see what it says. So here it is, BIP 342 consensus soft fork validation of Taproot scripts. It's by Peter Wolle, Jonas Nick, and Anthony Towns, and you can see that it's a BSD3 clause and so on. Let's look at the introduction. This document specifies the semantics of the initial scripting system under BIP 341. We covered that last week. This was Taproot, Merkleized subtrees, combining pay to pub key hash and pay to script hash, or pay to witness pub key hash and pay to witness script hash, essentially making it so that you can't tell which one is one and which one is the other. Motivation. BIP 341 proposes improvements to just the script structure, but some of its goals are incompatible with the semantics of certain opcodes within the scripting language itself. While it is possible to deal with these in separate optional improvements, their impact is not guaranteed unless they are addressed simultaneously with BIP 341 itself. Specifically, the goal is making Schnorr signatures, batch validation, and signature hash improvements available to spends that use the script system as well. So basically, there's a bunch of stuff in Taproot that require certain opcodes to change, and this is a separate BIP to talk about what opcode changes need to happen. So the design. In order to achieve these goals, signature opcodes opchecksig and opchecksig verify are modified to verify Schnorr signatures as specified in BIP 340 and to use a signature message algorithm based on the common message calculation in BIP 341. The TapScript signature message also simplifies opcode separator handling and makes it more efficient. So opcode separator has been around for a long time. It doesn't really get used, but basically this is going to simplify it. The inefficient opcheck multisig and opcheck multisig verify opcodes are disabled. So this was the main way in which we did multisig for a long time, but now with musig and Schnorr in Segwit v1, we don't need those. Now they're still in Segwit v0 and of course all the legacy stuff, pay to script hash and so on, but they are not in Segwit v1 as part of BIP 342. So that's good to know. Instead, a new opcode opchecksig add is introduced to allow creating the same multi-signature policies in a batch verifiable way. Okay, so this is a new opcode and it's going to allow for batch verification. TapScript uses a new, simpler signature opcode limit fixing complicated interactions with transaction weight. Furthermore, a potential malleability vector is eliminated by requiring minimal if. Okay, all right, so minimal if is going to be a new concept altogether, but basically it's not going to be considered standard. Well, actually, it's not even, it's requiring it, so I think it's part of the soft fork itself. TapScript can be upgraded through soft forks by defining unknown key types, for example, to add new hash types or signature algorithms. Additionally, the new TapScript opsuccess opcodes allow introducing new opcodes more cleanly than through op-no-op. So basically, they're going to be all basically like opsuccess or op-true or something like that, so that all the no-ops don't require like the op, I think it's like op-pop or something like that to get rid of the opcode that was there and so on. Specification. The rules below only apply when validating a transaction input for which all of the conditions below are true. The transaction input is a segregated witness spend. That is, the script pub key contains a witness program as defined in BIP 141. It's a Taproot spend as defined in BIP 341. Witness version is 1. The witness program is 32 bytes and is not pay to script hash wrapped. It is a script path spend as defined in BIP 341. Basically, it's not the pub key spend, it's the script path spend. The leaf version is 0xC0. The first byte of the last witness element after removing the optional annex is C0 or C1, making it a tap script spend. So it has to be specific to a tap script spend, then these rules apply. Validation of such inputs must be equivalent to performing the following steps in the specified order. If the input is invalid due to BIP141 or BIP341, fails. So it has to have a Segwit version. It has to be the length specified in BIP341. 141, and BIP341 specifically states that it needs to be 32 bytes, which is essentially a pub key. The script is as defined in BIP341. The penultimate witness stack element after removing the optional annex is called the tap script and is decoded into opcodes one by one. So the tap script has to be decoded. So it used to be that witness script was always at the end and redeem script was always at the end. Tap script is the second to last because you need another element for the Merkle going up getting the Merkle proof, basically. If any opcode, so you look at the tap script opcodes. Basically, if you encounter any of these opcodes, the validation succeeds. So it's basically like op success. And yeah, they're renamed op success 80, op success. These are all opcodes that really don't get used. And so all of these are op success, or validation immediately succeeds. And the idea here is that if you have validation, if you want to extend it in some way and you change this to something else, it becomes a soft fork and not a hard fork. If it's valid by old node standards, and then you upgrade this and change one of these opcodes, then it's stricter than that, so it becomes a soft fork. So that's the idea. Let me just check the comments real good. Okay, all right, cool. If any push opcode fails to decode because it would extend past the end of the tap script, fail. Yeah, and this is normal. If a push op script is putting data into the stack that's evaluating, if it goes past the tap script, it should fail. That means there's no data to do that push. If the initial stack as defined in BIP341, the witness stack after removing both the optional annex and the two last stack elements after that, violates any resource limits, stack size, the size of the elements of the stack, see resource limits below, fail. Note that the check can be bypassed using op success X. So there are certain limits to the stack size and the size of the elements, and there are more resource limits than that. If any of those are violated, then it fails. The tap script is executed according to the rules of the following section with the initial stack as input. If execution fails for any reason, fail. So the script has to evaluate to true or else it fails. If the execution results in anything but exactly one element on the stack which evaluates to true with cast to bool, fail. So basically, this was normal script evaluation. When it used to be that you could have lots of elements on the stack, and it could, if the top element was not 0, then it would evaluate to true. Now it's required to be one element, and it has to be non-zero, basically. If this step is reached without encountering a failure, validation succeeds. So there are multiple ways to fail and a couple of ways to succeed. So basically, op success will succeed every time. A lot of these other conditions are failures, but basically, tap script has to be executed in this particular way. Script execution. The execution rules for tap script are based on those for pay-to-witness script hash according to BIP141, including the op check lifetime verify and op check sequence verify opcodes defined in BIP65 and BIP112, but with the following modifications. So op CLTV and op CSV were introduced in 65 and 112, and they're part of Segwit v2 opcodes, basically. Disabled script opcodes. So opcheck multisig and opcheck multisig verify are disabled in tap script. The disabled opcodes behave in the same way as op return by failing and terminating the script immediately when executed and being ignored when found in unexecuted branch of the script. So once if you encounter either check multisig or check multisig verify, it fails. Consensus enforce minimal if. This is very interesting. The minimal if rules, which are only a standardness rule in pay to witness script hash, are consensus enforced in TapScript. This means that the input arguments to op-if and op-not-if opcodes must either be exactly 0, the empty vector, or exactly 1, the 1 byte vector with value 1. So minimal if means that you don't do op-if on anything other than 0 or 1. So that means that it has to be an explicit true or false condition in order to execute those branches. Otherwise, it's consensus enforced, so it's invalid if it's not evaluating a 0 or 1. Op success X opcodes. As listed above, some opcodes are renamed to op success X and make the script unconditionally valid. If you encounter those, then it's automatically valid straight away. Signature opcodes. The op-check-sig and op-check-sig verify are modified to operate on Schnorr public keys and signatures, see BIP340, instead of ECDSA, and a new opcode op-check-sig add is added. So basically, op-check-sig and op-check-sig verify used to check that the signature was valid according to the rules of ECDSA. Now it's according to the rules of Schnorr. So there's something else called op-check-sig add, which we will get to in a minute. Rules for signature opcodes. The following rules apply to op-check-sig, op-check-sig verify, and op-check-sig add. For op-check-sig verify and op-check-sig, the public key, top element, and a signature, second top element, are popped from the stack. If fewer than 2 elements are on the stack, the script must fail and terminate immediately. Okay, so you pop the top 2 off. One is a public key, one is a signature. You have to check, the opcode checks that the signature is good for this particular pub key, and that's it. And if there's fewer than 2, then it shouldn't work. For op-check-sig add, the public key, top element, C script num and second to top element, and a signature are popped from the stack. So there's not just a pub key and a signature, but there's C script num or some n. If fewer than 3 elements are on the stack, the script must fail and terminate immediately. If n is larger than 4 bytes, the script must fail and terminate immediately. That is like if it's greater than 2 to the 32nd, it must fail. So it's and can't be bigger than that. If the public key size is 0, the scripts must fail and terminate immediately. The public key has to be greater than 0. If the public key size is 32 bytes, it is considered to be a public key as described in BIP340. This is the y is a square trick to figure out, but it's 32 bytes, but it's a point on the curve. If the signature is not the empty vector, the signature is validated against the public key. See the next subsection. Validation failure in this case immediately terminates script execution with failure. So it needs to be valid, but basically the public key has to be the signature has to be valid against the public key. If the public key size is not 0 and not 32 bytes, the public key is of an unknown public key type and no actual signature verification is applied. During script execution of signature opcodes, they behave exactly as known public key types, except the signature validation is considered to be successful. So if it's not 0 and not 32, then we don't know what it is, and it's just going to let it through. And the idea is that we don't know what the signature type is, and later on it's going to be required to have some like we could have a soft fork if there's some optimization that we can have. If the script did not fail and terminate before this step, regardless of the public key type, if the signature is the empty vector for op-check-sig verify, this script must fail and terminate immediately. For op-check-sig, an empty vector is pushed onto the stack and execution continues with the next opcode. So false is pushed onto the stack. For op-check-sig add, a C script num with value n is pushed onto the stack and execution continues with the next opcode. So if the signature is empty, then you just put the n back and then you just keep going. If the signature is not the empty vector, the opcode is counted towards the sigops budget. See further. Op-check-sig verify, execution continues without any further changes to the stack. So basically, the check signature is valid or not. If it's valid, then it continues. For op-check-sig, a 1 byte value 01 is pushed onto the stack, so it's true. The check signature is valid, so it puts a true on the stack. Object SIGAD, a C script num with a value of n+1 is pushed onto the stack. So basically, after it checks these signatures, it increases the number so that we know if that one was in particular good, and that way we can count up the number of good signatures in this, and this incrementation is how we determine if there's this is the replacement for object multisig. Signature validation: to validate a signature sig with the public key P, compute the tap script message extension ext consisting of the concatenation of the tap leaf hash, key version, code separation position. That last one isn't that important, but it's a tap leaf hash and a constant value. That tells you which position it is in that Merkle-wise tree of tap scripts. If the sig is 64 bytes long, return verify p hash tap sig hash, where verify is defined in BIP340. So it does the normal schnorr verification there. The sig is 65 bytes long and the first byte is not 0, then you do this other one, otherwise fail. In summary, the semantics of signature validation is identical to BIP340. So in other words, it's validating that it's a good schnorr signature, except for the following. The signature message includes a TapScript specific key data key version. The signature message commits to the executed script through the tap leaf hash, which includes the leaf version and the script instead of script code. This implies that the commitment is unaffected by opcode separator. The signature includes the opcode position of the last executed opcode separator. In other words, it's using schnorr signatures with Taproot basically. Resource limits. In addition to changing the semantics of a number of opcodes, there are also some changes to the resource limitations. Script size limit. The maximum script size of 10,000 bytes does not apply. Their size is only implicitly bounded by the block weight limit. Okay, so it's no longer 10,000 bytes, so you could have a really, really large script if you want. But the block weight limit is 4 million, so it has to come under that. Non-push opcodes limit. The maximum non-push opcodes limit of 201 per script does not apply. So you could have lots and lots of opcodes in a particular script for Segwit v2. SIGOPS limit. The SIGOPS in tap scripts do not count towards the block-wide limit of 80,000 weighted. Instead, there's a per-script SIGOPS budget. The budget equals 50 plus the total serialized sizes in bytes of the transaction inputs witnessed, including the C compact size prefix. Executing a signature opcode, object sig verify, or object sig add, with a non-empty signature decrements the budget by 50. Okay, so any of those opcodes will decrement it by 50. If that brings the budget below 0, the script fails immediately. All right. So basically, it's 50 plus the total serialized size in bytes of the transaction inputs witnessed. So, however many bytes that is, you get. So a typical signature is like 64. So if that brings the budget below 0, the script fails immediately. So you can't have like multiple object sigs and like 60 like under 150 byte. Well, you can't have two check sigs with and be under 100 bytes in witness, which makes sense because you would need at least 128 bytes for two signatures. Otherwise, you're just sort of repeating yourself. So it's a relative weighing basically instead of an absolute weighing, and that makes sense. Signature opcodes with unknown public key type and non-empty signatures are also counted. Okay. Stack plus alt stack element count limit. The existing limit of 1,000 elements in the stack and alt stack together after every evaluated opcode remains. It is extended to also apply to the size of the initial stack. So can't be more than 1,000 elements on the stack and alt stack. Stack element size limit. The existing limit of maximum 520 bytes per stack element remains both in the initial stack and in the push opcode. So you can't have an element size that's bigger than 520 bytes. All right, so that's about it. It looks like it's marrying Taproot and Schnorr in a way as to make them and describes basically all the rules. It looks like opcheck multisig and opcheck multisig verify are basically deprecated, or I mean, no longer work for Segwit v1, and you got a bunch of success elements on stuff that no one was using anyway. So that's basically it for this opcode. Let's see if there are. Let me see if there are any questions. Well, thank you, Seth. Perhaps view counts will be the same as they are for TA videos, but this is the real value here. Not everyone can do what you are doing for us. Really appreciate it. Well, thank you, Seth. I do feel like I would. Oh, I see. Okay, I didn't put the audio input device. Give me 1 second. All right, now you guys should be able to hear me. Do you guys hear me? Okay. Well, yeah. Thank you, Seth G, for what you said. Yeah. Okay. Now you hear. Yeah. So I forgot to see. I don't know this software that well, and basically it's screwing me over. All right. Anyway, thank you, Seth G. I know that this isn't TA. I would love to do more videos like this where I explain various BIPs and white papers and whatnot. If you guys like it, please pound that like button and share this video. And let me know in the comments what other things I should cover, whether it be different BIPs or white papers or something like that. I would love to have a regular feature, White Paper Wednesday, for you guys and explain different things. Anyway, that's it for me in London. I am going to be speaking at the Advancing Bitcoin conference here in London tomorrow, and yeah, it's like almost 9 p.m. here. I think it's like 2 p.m. back in Austin where I live, and I don't know, and you know, it's around mid-afternoon for most of you. Yeah, so anyway, Bitcoin's going crazy, so of course people are really interested in price. I don't know, maybe at some point I'll do like some sort of like a stock to flow show or something like that. But yeah, I don't know what else is interesting to people. Anyway, hopefully that helped you. Fiat delenda est. This